喂啊，冇問過，佢 reimburse 咗俾我，咁我琴日已經係搞掂咗嗰個已經。哦，佢第一個 OK I guess yeah you will. I'm asking the TA to handle that part. Yes, you will be doing the reviewing your classmate. I have asking the TA to handle the thing. Yes. So the homework 2 will be due the next Friday. So and then after the today's class, we'll finish the estimation. So we will have a quiz next Tuesday, and the homework 3 will be assigned by then also. So today's goals we'll be talking about estimation, and then we'll touch on some hypothesis testing. But before that, any question before we proceed? The reason that I haven't announced the exam days, I don't know whether we will resume online class or not. So I need to figure out that. But likely that we will do the quiz at after we finish all the content, then we will be doing the final test. I guess that would be. I mean, we're still aiming at the last week of November, but I'll figure that out soon. Because we need to finish everything before the test, right? So that is one constraint we have right now. So I guess now that we should start if you don't have any questions so far. I guess we should get started. So some question here. The quiz will be covering sample distribution estimation, two part, because I guess that would be they are so related, so that's why I combine them together. Yeah. Maybe 2 part together. And also because of we are a little bit time constrained, so we need to cut one quiz. You'll be using the latest edition, but already included the question in the PDF file. But you can, already included another PDF file. Fayan, is it clear? I think I included there. Yeah, all the quiz are participation based. Yeah. So I think if you miss, I think I just take out the best out of this, right? So if you miss some of them, I think it's okay. Yeah, just participation, yes. So I've been using the 8th edition, but I think for those of you who don't have a copy or have some reason cannot have a copy, I think I make it available there. I think I mentioned the class is 19, right? I don't know. I'm not sure if you are in the last class, but I think I'm pretty clear that when I talk about this 19, probably you can check back this video we talk. I think when we talk, we explicitly make it very clear. It's in 19. There was a typo there. You can check it back if you. Any more question? Feel free to ask. If no, then we will be someone asked me Yeah, if you compute from Excel, if you want to skip the step, you can say you are following using Excel this function and this is the result. Yeah, if that is uh, if that's the case, I mean, you use Excel, then you from there, then you can use Excel function. This is the result. You just tell for homework, tell me how you arrive the answer, right? So probably you can tell me what the Excel function, what you input to get it, then that will be fine. Because I want to make sure that you're not copying from each other. That's it. I mean, in case of doubt, then I will ask the TA grading it, who will ask you to clarify. Otherwise, it should be all okay. But yeah. So let me know if the homework is too hard or too easy or too few questions. I can give you more if needed because many of you asking more exercise. If needed, let me know. I can assign you more. It depends on the TA, so I'm not that sure yet. Yeah, I think this TA will give you the answer. I will confirm TA again because these days it's hard to get in touch with people, you know. But I try to get it as soon as possible. Okay, is that fine? Any more question? If no, then we just review the estimation first. So last class we covered estimation and what we are doing in the estimation in the sense that is we want to guess what happened in the population, right? It's like I want to know what is average income uh, in the economy, or what is the average expenditure on that product. Then I want to know this amount, but how I do a survey, right? It's for marketing people, right? You want to know how this going on, or if you are auditor, you want to the same idea for finance. You want to look at some people look at the past history to try to predict the future uh, move on the stock, right? So that's the same idea. Uh, so you care about mean or variance, and the estimator is the way you want to estimate what lies in the population, and that usually relies on the sample size, right? And uh, there are two ways you do an estimate, right? The point estimate or interval estimate, right? And we learned that the good property of estimate is unbiased efficiency. Compared to your slide uploaded, I take away the consistency because I think that would be too technical and we don't use it for our purpose. So that's why we just basically skip that for a more technical definition, because to define consistency, you need a more technical definition, and I guess we don't really need it for our purpose. So the next thing is about the point estimate, right? And the most common case we care are population mean and population variance. And the natural starting point is we have the sample mean and sample variance. And we have been using it, right? And then why we have this and why n minus 1 and why we have 1 over n, but not other way around. And first we saw that both of them are unbiased, okay? So that's why I justify we use n minus 1 more than n. And you notice that the n and n minus 1 do not make a much difference when n is large, okay? But still when n is small, it will make a big difference. So that's why it's still important. And you also may ask why is use a simple average but not other weighted average, right? And we did so that a technical notes that if you use other weighting scheme, that will lead to bigger variance, okay? So sample mean is the average arithmetic mean, the simple average is the best among all any weighting scheme. So that would be the goal we have. And sample proportion again would be the same because it's sample mean, right? So that's why it's also a good estimator. And then beside the point estimator, we want interval estimator, right? Instead of asking a single point. And here we only focus on sample mean. Okay, we are not doing the interval estimate for the variance. Okay, uh, because most of the time we care about the sample mean. Okay, and we know this at the end of the class, right? This is the uh, confident interval estimator, right, or interval estimator, which says if you want to estimate sample mean, but instead of asking the sample at one point, you ask intervals, then you would give an interval that is centered about the sample mean, and you go up and down by this margin, right? The margin will be decided by because it's a standard normal, right? You have this z of alpha over 2, and based on the variability of uh, the population, right, then you say sigma over root n depend on sample size. Okay, so if we know this, right, then or we have some knowledge about this, then we are done, right? And this formula is not very useful unless we know sigma, right? And in the most cases, we don't know sigma, right? So this is just for hypothetical users, and most of the time, uh, uh, you'll be using this T, right? Basically, this is the formula that you use that you will be estimate based on the sample mean, right? And from the data, you have the sample variance, right? And based on the sample size, you have the T distribution, right? With degree of n minus 1, and this d root n, okay? And this is the confidence interval when you have unknown variance, which you don't know. And this is I would say this is the one that you use all the time, right? Because we collect the sample, depending on the sample size we have, then we compute the S, compute the X bar, and that's it. So that is the things we do. And that is the most important, I would say, the formula in this chapter. But before we proceed, I mean, let me a question, and those of you actually point out that the one uploaded has a typo, and actually we correct that at the first time when we see it, right? So it's 19, right? It's not nothing because it's n minus 1, so it's 19. Just make sure that you get it right. And we already shown you how to do the Excel. In case you missed the last class, please check the Excel. Please check the video to see how we operationalize everything there. Okay, before we start, any more question? For those who are arriving late, we'll be finishing off this chapter quickly and then soon, and then we will be having quiz for this chapter and the last one in the next class. So someone asked me why alpha is like this. So this usually we'll call 1 minus alpha. The reason will become clear soon because next chapter we will give you some idea what's alpha. And that's why this is alpha over 2. Okay, so you'll become more clear why it's alpha very soon. So don't worry about that. You will be clean. You'll be very clear later. And just to remind you again, what is Z alpha? Is asking here that the right tail is alpha. Okay. So the reason why we have this is if we want the center is 1 minus alpha and symmetric. So that's why the both side is alpha over 2. Okay. So any more question? Because I would be happy to listen your question, right? Because next class, I mean, next Tuesday we'll have a quiz. So anyway, you will know whether you don't know or not, because that would be a great opportunity to let you train yourself whether you know it or not. Any question? Any further question before we proceed? Okay, if no, I mean, it's okay. If okay, please type okay because I make sure that everyone knowing what we're going on here. I mean, since we have good. So very last thing is thank you. If we have binary data, right, with proportion data, which data is either 0 or 1, right? It's binary data. And if you figure out that given your sample size and okay, and your sample proportion, right? This is x bar in that binary case, and both of them are more than 5, okay? Then we can use the following interval estimator, okay? Is the P here, okay? And this is P times 1 minus P over N. This is the variance of sample mean, okay? Because when P is for binomial, mean is P, right? The variance is 1 minus P, right? And then the variance of the mean will be this, okay? Let me repeat if this is each observation, right? The mean, say xi, right? The x bar, it's this guy, right? It's unbiased. And the variance of each observation is P1 minus P, but the variance of this x bar, okay, will be 1 minus P over N. Okay, this is, do note that is also same as each expectation here. So each observation expectation is same as the mean. Maybe I write down here again to make sure that for each observation, right, would be, maybe I should be a little bit more formal. So if the population, right, follow a binomial pi, right, and this guy will be pi, right, and the variance of this is pi 1 minus pi, right, and if you consider mean of this, right, so suppose this, right, this is still pi, but depend on n you have, right? Okay. So that is the idea. And because bigger than this, at least 5, so that's why you can use normal. Okay. So that is something we mentioned. And we don't need to estimate the sigma, right? Because the sample proportion can be replaced by this. That is a good estimate. Okay, so just a special case. In case it's still not clear, the next example will become very clean. Okay, so in this example, I have a sample proportion. Okay, a random sample with binary data, right? With sample size n is 64 and p is 0.3. This is come from the sample proportion, right? So there's nothing we need to know for the population. Okay, so that's very convenient. It's different from the case where you only have the data that is more than 0.1. Okay, then you need to know the population variance in order to use the normal. Okay, so this point estimate, right, would be sample proportion, right? That would be unbiased estimator. And from the table, this is 1.96. For those who forget, there will be how to get that is norm S dot inward and 1.9. Sorry. So we will be, because this one gives the tail, so we need to be careful how to get it. Okay. This is 95%. Okay. Or 0.95. Okay. This, right? That's symmetric. So this is 2.5%. This is 2.5%. Okay. So that means from here up to here is 97.5%. Okay. Sorry. So that's why you need to put 0.975 to get this number. Okay. If you input norm as inward, you put 0.025, you get negative 1.96. Okay. Because you are getting this number, because it's centered at 0, you are getting this number if you get this one. Okay. So just make sure that you get the positive negative correct. And the margin of error, right, will be the Z, which is this number. And this is P times 1 minus P over N. Okay. Take square root. So that's why 64 here, 0.3 here, 0.3 here. This is 0.1122. Okay. And you add and subtract this one from P, that would be the answer. Okay. Just to remind you that a little bit, for this sample data, right, it is possible that P minus ME, okay, can be less than 0, or P plus ME can be bigger than 1, okay? And usually that means rubbish, right? Because P cannot be bigger than less than 0, or P bigger than 1 will be problematic. There's no special way to prevent that happen, okay? And in that case, we still write as such, but usually that would be not very meaningful. But for convention, we still write in this way. So we still have interval from that, but if you're less than 0, then probably you would want the LCL start from 0. But for our convention, we just follow the definition. Okay, we just, if negative, we just still keep it negative. I think it's still fine for our purpose. Is that okay? Any question? Any question? If no, we are going to the very last part of this chapter. Any question? No? We're going to the very last part of this chapter is sample size. Okay, this will be very useful for those actually who are doing audit. Okay, and then you okay, consider the following. Okay, so far we have saying the sample size. You can write as well, but usually for our purpose, we just because we define this way, we don't have a minimum maximum, so we just write less than 0, still just write. It's okay to write negative or 0, up to you, but because we define this way, we don't want to complicate notation, we just keep negative. Just but usually don't have this problem. But it's possible to have this problem. So, but just let you know, I mean, you have to figure out what to do when you're less than 0. But for our application and introductory class, let's leave it as negative, just to for purpose. Of course, you need to figure out how to do about that when you're in that case. I mean, most likely it's because of your sample size is too small, then it's not precise, so that's why you have this problem. And otherwise, you don't have this issue. But I mean, actually, what you do the question is, what do you do in the real world, right? Probably this is the question you're asking. Okay, in that case, you should increase your sample size to reduce the variability. That would be the thing that you should do. Does it make sense to you? Okay. So for the sample size, let's go back to here. Is you want to say do an audit, right? And then you want to check whether there's enough inventory there, right? Because you go to a warehouse, right? Maybe the firm tell you, oh, there's an X number of stock here, okay? You want to check whether that's correct or not, right? Or they tell you, oh, are there how many things are there, or on average, how many stuff are there? You want to know whether they're right or wrong, right? And how many sample you want to get, right? And is you have a audit or what is a risk-based assessment, right? You want to see if what's the size of error you allow, right? Suppose you want to say, right, X bar, right, is within how many variability you want to allow it to happen, right? That is the design of it, right? Maybe you want to allow it within 10% of mean or 20% mean or so on and so forth, right? And the simplest is you have to decide how the margin of error you're wrong, okay? The margin of error can depend on the sample mean if your prior knowledge about the mean, right? But we will be fixing the idea of some ME. To decide the width of the interval, right? How you decide this, how large error you want, maybe depend on the population mean you are thinking, right? Say, suppose you say, oh, someone claim the mean is like 10, okay? You want to say, okay, I want to make precise. It's okay to be 9.9 or 10.1, I think it's fine. And in that case, my margin of error is 0.1, right? Or you want it to say, I only want it to allow it like 5% error, right? Then I won't only allow 5% error, I mean 10.5. So 5% error is 10.05, right? And 9.95, you allow 5% error, right? It depends on some idea that or some rule that you justify why you need this margin error, okay? And given this margin error, okay, and under central limit theorem, the margin of error, remember, is this, right? This is the formula that we have, okay? And this margin of error is sometimes, as I said, is given by application, right? I want it to be as precise as this, okay? Then that's how you achieve this goal, right? Is to reword this, make n the subject, so you get n here, right? You just change to root n equal to z alpha over 2 sigma over me, right? And you can square both sides because they're all positive, right? So that, oh, I think I missed a square here. So there's typo, just make sure that you see this. I think there's a typo over here. There's a typo over here. So make sure you notice the typo and don't ask me again next class. So the typo here, so it's a square. So z square over sigma square over me, okay? So once you decide the level of confidence, maybe 90%, okay? Or 95%, or 99%, that is a free number that usually you want to have, okay? And if this is a margin error, that is, as we said, how we decided. And then once you have that, if you have any knowledge about this sigma, also we make some assumption, or we know it, and then we can decide how much sample we need, okay, to get. Okay, that is that is a thing that we want to get it to make sure that everything falls into control, right? So go back to this question. Is that clear what we're doing here? So to repeat, what we are doing is someone try to, I want to get some precision, okay? How much n I should got, right? Because you don't want to waste too much effort, right? And in that case is, okay, how much precision we want. We give the precision, maybe 0.1, maybe 0.3 or 0.4, or depends on your prior knowledge with ME. And then depends on how confidence you want, right? You decide, you give you the Z, okay? And that tell us how many sample you want. And once you get a sample size, you go there and do the sampling. And then that will give you a good estimate. Okay, that is the idea. You decide how much sample you want to get. Okay, and you should do it before you go to the site, right? You go to the site and you decide how to do it. Same as you do research, right? Before the research, you decide the studies. Is that clear? What we're doing here. Okay. If this is clear, then we go to example. I think the example will become even more clear. So for somehow we know the standard deviation is A. How it comes about, we I don't know, some from history or some from data, or there would be some way to determine this. Okay. And this is your choice. You want 95 confidence. You want within population mean is plus minus 4. Okay. This is based on assessment, right? If plus minus 4 is okay, maybe you decide this coming from the 8, right? You want it to be within half of SD, that would be safe. Okay, that is something in your mind. Okay. Or there's some other criteria to give you the idea you want this within 4. Okay. And just to remind you again how we get this, right? Probably you remember, right? It's norm as inward 0.975. Okay. And marginal error is 4. This is given from here, right? And then you need how many sample we want, right? This is this guy, okay? And I guess a typo here. Sorry, the typo. I guess it. Should I change the answer or change the question? Anyway, just change the answer. I think it's better to change the question, right? Then I don't need to change the answer. Yes. Let me confirm that is right. 1.96 square times 10 square over 16. Maybe I use Excel. Maybe it's good to do Excel together here. So we have 1.96, we have 10, we have 4, right? M is, maybe just do it here, M is 4, right? And SD is 10, okay? Z is 1.96, okay? And then the sample will be equal to basically is Z square times square divided by square. Okay, so okay, so that is that's correct. I guess the problem is the question. I guess you can see what's going on here, right? Is that okay how you see the formula being calculated? Can you see Excel? Yes, can you confirm if you can see the Excel spreadsheet? Good. So that's how we calculate the N is 24.1. So sorry for the typo, just to remind you that this should be 10. Okay. This should be 10. Sorry for the mistake. And then you can see we did 24.101, but that means we need 25 sample. We just run up. Okay. because 24 will not be enough. So that's the idea. You can decide how many samples you want. Is that okay? Good. And the other way around is suppose we know the population proportion, okay? And we know the variance is p times 1 minus p, right? And the sample mean of that will be pi times pi over n because this is sample mean, right? And central limit theorem tells us this is the case, okay? You go n again, I think this is square missing, okay? So that would be the same, right? We just, this will be equal to root n equal to c over 2 pi 1 pi root over me. And then you square both sides, that is the answer. Okay? And let us look at the, is that okay? If that's okay, let us look at the example, okay? So history said the population proportion is 0.4, okay? So that's pi is 0.4. And then the sample size, right? 95% confidence. The sample mean, or actually the sample proportion, I guess. But the same thing here because we have the proportion data. So sample mean is population proportion. Okay, we want it to estimate the sample mean, sample proportion, which is within plus minus 1%. Okay, and so in that case, we look at the population variance. Is pi times 1 minus pi is 0.04, okay? And this is very well known, I guess I don't need to repeat, it's 1.96. And the margin of error is 0.1, that is, we put it here. Then it's 1.96 squared times 0.04, 0.24, and then 0.1 squared, so we need 92.19 sample, okay? So that means that to run up, right, we have 93, then we will get what we want, okay? That is what usually when you have binary data, right? This is very often, right? We ask maybe whether people interested in the product, or now the political election, whether people support this or support that, okay? That is something commonly used, okay? Or want to check if the proportion of the good is bad or good, okay? So that is something along that line. But so that's end about this chapter. So let me know if any question of this chapter. Because we will quiz for the estimation and the sampling distribution next Tuesday. So the question is how do we not using NP1 minus P, right? Someone asked, what if this is not true? Very good question. So remember this, what we're doing is normal approximation for binomial, right? Is it, remember this part, okay? So what they're actually doing is like this, right? This is actually a binomial distribution, right? And now you wanted to assume this is normal, okay, by saying that binomial NP, right, convert to normal NP NP1 minus P, right? That is the case. Then you can convert it to there, right? And of course, when you have mean, then you over n. So that's how you get all this number, right? And how do you get it is now instead of normal, okay, you have used the binomial CDF, okay, binomial. So you use, I think the Excel have the binomial inward to do that part. So it's no longer normal, it's a binomial. So you can just assume binomial and do the same trick. Does it make sense? But for your purpose, it's no problem, because for our assignment or for our elementary, we can use that part. Okay, but this is a very good question, because it's not then you will follow other distribution, then you can use the same trick. Well, when you ask proportion, it's binary, right? It's just either whether you like it or not. The question that, so I have a question people ask, some of you ask me, how can I know it's proportion or not? When I say sample proportion, it's already binary data, right? If proportion already, because proportion is already sample, is a sample mean, right? And only the data is 0 or 1. There's only difference. Unless they ask you, unless they explicitly tell you there's a binary data, then it's not binary. This is by default. Yeah, but actually there's not much different, right? I mean, you can see this. The only difference is like when it's a binary data, then you can estimate the variance directly, and then things become more straightforward. Otherwise, the same trick applies. I mean, you can also, even if you are not binomial, you can apply the same thing, use the t, but that would be less accurate, right? Because you don't need to use t. That's the only reason why you have that here. Is that okay? That is very good questions. And any more? If no, then we still have 2 minutes. Then maybe I just give very brief idea about hypothesis testing, and then we'll break. So, what this chapter is very closely related to what we learned. Okay, so you can say this almost, I mean, in terms of calculation, it's almost very closely related to what we have just learned. Okay, what we just learned is interval estimation is, okay, population, okay, we have the population, we care about the mean, right? The mean. Okay. And now we have some sample. We get some sample from here. Okay. This is called the sample. Okay. Based on sample with a sample mean, X bar. Okay. And then we know the interval estimator, which is plus minus Z over 2, sigma over n, root n, or X bar plus minus T n minus 1, alpha over 2, S over root n. Okay. So this is to estimate. Interval estimate depending on whether you know sigma or not. So the question is, go back before, okay? We use this to estimate mu, right? And the reverse question is, if someone tell us, okay, claim that the mu is some number, okay? And based on evidence you collect, can we have any say about this statement true or not, right? You try to evaluate whether this statement is true or not, okay? And the idea is very simple. If the mu fall within the interval, then you will have think that the claim is supported. If what they claim is outside, that's not support. Okay, so basically this is about this class. I mean, it's about hypothesis testing. It's trying to see if what people claim is inside. If inside, then yes. Outside, then no. Right? This is a rather simple idea because if this is true, right, then we should have seen this would include what we have estimated. If not, then it's unlikely that to be true. Okay, so application would be, as we said, right? You go as auditor, right? Someone claim this is the case. You check the data. That's not the case. Then it can't be true, right? So that is the idea. Same for proportion, right? Someone claim the population proportion is pi, right? You look at the sample, go to the sample and calculate p plus minus CR over 2 and p1 minus p over n. And you try to see if the p is within the pi. If yes, yes. If no, then you have some doubt about the claim. Okay, so that is hypothesis testing is testing those claims on the population. Okay, but I should give a break now, and then we come back. So let's just a break. Break until 1:32, I guess. Okay, so see you then. Answer any question that you might have. Before we start, any question? If there's no question, then we continue. Okay. Just to recap, what we are doing, we just said is we have an interval estimate, right, based on sample mean, right, or the sample proportion, right, with some margin of error, right. This would be the interval estimator, and we want to check whether mu is inside or the pi population proportion is inside. If that's the case, then we would say that is something that support. Otherwise, it's not support. Okay, so that is the main idea. But we give a more general background for this. Okay, so let's start with one sample. So this consider we have two actually correspond to two parts of the textbook. So we divide it into two parts. One is one sample, the other is two sample. And later you will see why we divide these two, but that is done in this way because of the complexity of the problem. So what we are doing is trying to test a claim is supported by a sample or not. Okay, so that is that's the goal, whether it's supported claim by the sample. Okay, and usually we divide it into two parts. One is the null hypothesis, the other alternative hypothesis. Okay. Null is usually the claim that we want to check whether it is true or not. Okay, this is the claim we check. Okay. And usually we'll claim the alternative one when the null is rejected, this alternative. Okay. So you can see actually they're asymmetric. Okay. So they do not have the same standing, right? So null is something is different from the alternative, right? Null is something that if the data is not rejecting, okay, then we'll keep the null. Null is always the one that is a status quo, okay? In terms of, say, the judicial system, in the courtroom, right? In the in the British or the common law case, right? The null hypothesis is assume the defendant innocent until proven they are guilty beyond reasonable doubt, right? So this is like, right? This is more like guilty, right? This is not guilty, right? This is or innocent, right? You innocent until until you're proven, right? So of course, in other jurisdiction, right? People swap, right? Some other jurisdiction, not common law, right? They would do the other way around, right? You have to prove you are not guilty. So that's another issue, okay? But so that's why they now have some special status, right? Because you have to prove beyond reasonable doubt, okay? Otherwise, we assume now is correct, okay? And you do notice that swapping them is actually a very different case. So the same as statistics, that will be a very different thing if you swap the two. Okay, and we reject the null. Okay, but we will not say we're accepting the alternative, but we're just saying that we are whether we reject. We never say never accept which one. What the terminology is whether we reject null or we fail to reject null. Okay. So we never say we accept null or we accept the alternative. We never say accept. We always whether say we are reject or fail to reject. Okay. The reason why because we can never confidence that this because we always doing sampling. Okay. Sampling with sample error. So we are never 100% sure. Okay. Never 100% sure. So what we can say is reject or fail to reject. Okay. Is that clear? At this point? If okay, can you type okay? Good. So just to minor thing is called H0 or H null purposes, or H naught. Okay, this H1 or HA depends on which textbook you're using, but we use H0 as the null and H1 is alternative. Okay. So for our purpose, there will be two types of hypothesis. Either you call simple or composite. Okay. Simple means is equal to particular value, like mu equal to this or p equal to 0.5. Okay. So not p because we are talking about population. So it's pi equal to 0.5. Okay. And within some interval, maybe mu is bigger than 3 or mu or less than equal to 3. Okay. Or pi is bigger than or equal to 0.5. Okay. This. Okay. For the purpose of this class, we focus on when we talk about null hypothesis, it is always simple. Okay. The alternative way is very complicated. Okay. So we are just scratching the surface of hypothesis testing. This is a very complicated topics to be covered, but we're just focusing on the simple case that will be suffix for most of our application. Okay, so so we have simple and composite. Okay, so we said we also focus on only simple null hypothesis. Okay, and that another distinction about the alternative hypothesis, right? Alternative, we are focusing on composite deposit. Okay, so now it's always simple. Alternative is in our case is always composite, and there are two ways to put composite. Either is two-sided or one-sided. Okay. And say suppose the null is mu equal 3. Okay. So what are two possible alternatives? Okay. One is not equal to 3, and that is the most direct. The other one is mu is less than 3. Okay. Of course, the other one is also, we didn't write down, is mu bigger than or equal. Sorry. Okay. So it should be, let's forget about this. Equal should be less than, to be more precise. So more than or less than. Okay. So there are three possible ones. Okay. And you may ask which to use in what cases. Okay. It really depends on application. Okay. Suppose you are asking to see as an auditor, right? You're asking to check whether this number is correct or not. Okay. And any deviation of that will have a big consequence. Then you'll be asking to do this. Okay. Will be not equal to. Okay. And suppose you are application in terms of checking the quality. Okay. And someone claim, okay, the probability of the product is not defective is 0.9. Okay. And as a quality control, okay, you would only care if the, oh, sorry, not P, but should be pi. So this is the non-defective product, right? The rate, okay. And you only care about this rate is less than 0.9, right? As a quality control, okay. More than 9, you don't really care, right? More than 9 actually is a good thing, okay. So only then you would jump up and do action is when you have less than, right? Then that will be the issue for you, okay. Or if you are auditor, you are talking about the bank's say default rate, right, for some credit card, right? Say maybe 0.8, right? And then you don't really care if the default rate as you audit the company is less than 0.8, right? You would care if it's more than 0.8. Okay. So whether you put one side or two side depends on what is the consequence of that. If you care about whether both side deviate would be important, or you don't have any knowledge about alternative, then you would do that. Or if you have one side is enough consequence, then you would do one side. Otherwise, you do both. Is that clear? Is that clear what we are doing here? Okay. If no question, then we go to the other slide. Okay. Sorry, there's a non-definition because it's a completely new, we have a completely new terminology. Okay. As we promised, there's an alpha. That's why now we're explaining some alpha here. Okay. So this is what we call a general idea of making a decision based on statistics. Okay. That is called statistical decision. Okay. Making decision based on random sample, right? Because samples with randomness, always you would involve two errors, okay? In hypothesis testing, okay? We have called two type errors, okay? And so if the null is right, but you reject it, then it's a type 1 error. So rejecting the correct null, okay? That is, null is true, you reject it, okay? And we will write this as alpha, okay? Later you will see why this alpha, okay? And this alpha, in terms of terminology, this is all called level of significance, Okay, in later you will see what's this. And type 2 error is the other way around. The null is wrong, but you fail to reject. Okay, you didn't reject it, so it's false. You didn't reject. It's called beta. Okay, and as we would expect, 1 minus alpha is called confidence. The same terminology we use, 1 minus alpha. And beta is called power of the test, okay, or simply power. Okay, is that clear? Just definition, nothing but definition. Okay, so to give you a more clear understanding, let's give you the following diagram. Okay, so you can see that actually there are 4 situations, right? Either the null is true or null is false, right? And then you reject the null or not reject the null, right? If true, and then you reject, then you have 1 minus alpha, right? And you reject it, is type of error is called alpha. If this is false, then there will be the probability of committing this error is called beta. And the probability not committing this error means that you correctly reject is 1 minus beta. This is power, right? If you recall, right? And this is what we call the confidence. Okay. And later you will see we can choose any alpha we want. Okay. But for given n, okay, given sample size, there will be trade-off between alpha and beta. Okay. In the other words, if I give you alpha, okay, the beta can only reduce by making n bigger. Okay. So basically the trade-off between alpha and beta. If you want smaller alpha, then you have to be a bigger beta. Okay. In that sense. So that's why it is not, although you can choose alpha, it's not always the case that you want the smallest the better, because beta will be bigger in that situation. And do remind you that alpha is the probability that you commit type 1 error, which means that even though the null is true, you reject it. Okay, so that is the something you need to remember from the first 7 slide. Okay, alpha, okay, is the probability that given h null is true, you reject it. Okay, if it's true, you reject. So there's something you need to remember, and this is the thing that I'll be using. We will not talk about beta at all from the from the rest of the slides. Just remember alpha would be the best thing. Okay, and then you need to remember what's now what's alternative, but it will become more clear and clear soon. And the question, just some terminology. So there's nothing to understand whether you know it or not. Okay, there's nothing to no analysis. It's just something to remember. Okay. Then proceed. Okay. So this is the standard procedure we'll be doing for the rest of this slides. Okay. So that is always when you test a procedure, is always the first step is you have to state what are the null alternative, so which is x0 and x1. It should be clear when you write down the problem, and you construct test statistic based on what a sample outcome is. Right, sample outcome means sample mean, sample variance. Right, if proportion will be this sample proportion. Okay, sample outcome. And test statistic, later you will see what are they, but it would depends on for the case of we have hypothesis about the sample mean, okay, it will depends on whether we know the population variance, okay. It will become more clean later, but we will construct the test what called Z test and T test, okay. As you expect, if we know this, then we'll go for this. If we don't know, if you know, we go for Z. If you don't know, we go for T, okay. So that's later you will see this closely related to what we said about the interval estimator, okay. And then based on the distribution of statistics, okay, actually based on the alpha, okay, you will construct the critical value and p-value, okay, and then you compare this with alpha, okay, and or the critical compare this case with the case 2, okay. This is the making decision, okay. Here looks a little bit tricky, but we will go immediately into the example, then you will see, okay. But later you refer to this slide, then you will see what's going on, okay. Currently now it's not very clear what's going on here, but let's revisit this afterward, okay. So as we said, if we know this, we use Z. We don't know, we use T. Why? The reason is if we know this, we know that X bar will be normal distribution, right? With mu and sigma square over n, right? And then we know this is the case, right? Just to remind you, this is normal CO1, okay? And if this is not the case, we will use S over root n will be Tn minus 1, okay? So that will be the main idea we call Z test and T test. We will immediately tell you the procedure to do it. It's very procedural, okay? So it's something not difficult to understand, but is very standard, okay? So this is the procedure, and then we'll explain why that's the case, okay? So as we said, we'll focus on the case where we have simple now. So I think for the simplicity, you can ignore this, I guess, because we said we always focus on simple hypothesis. So you can ignore that particular statement. Okay. So what here is the question, the procedure is the following. So someone claimed that the mu is particular number A is a number, maybe 5, 12, or some number, okay? And then you want to say, okay, if this is rejected, I would rather say this more than, okay? So which essentially say if it's less than, it's not our concern, okay? If more than is a concern, maybe you can see mu is the maybe product control, right? That may be the percentage of germs or a percentage of harmful substance in the food or other product you are selling, okay? More than a certain level, then you will raise alarm, okay? So product control. And suppose we know this, right? And given the sample mean, given the sample size, right? We know this follow normal, right? This is nothing new. We want to see whether we can support this or not, okay? The idea is following. Suppose this is true, okay? This is true. If this is true, we should have following, right? The X bar will have the following distribution, right? By central limit theorem, we have the sample we have the mean of the sample mean is the population mean, right? And the variance will be sigma squared over n, right? And in the other words, you can rewrite this into the z, maybe right here, into the z thing, right? Rather than z, which is 0, okay? And now we are saying that if the evidence showing that's way positive, then we alarm, right? And what it means is, if it's big enough, then we would say we want to reject it, right? Because if big enough, then it raises alarm, then we don't want to hold our original hypothesis that is equal to A, right? So mu actually is A here, right? But in that, here is 0, right? If this is way positive, then we would be not willing to say the evidence supporting the claim, all right? It's not supporting, okay? But how much more we want to say above 0, we want to say there's a problem, right? And we want to depend on the probability that's happening, right? We'll say this is alpha, right? And this is, the smaller the alpha is, we will be more stringent in our rejection. We are more careful if we have a small alpha, okay? And that, I hope that explains why we call alpha in that case, because this is, alpha is the area that you would think you would reject, right? It's the small probability that you would be not comfortable with, say, this evidence supporting this, right? Okay. So basically what you are doing is, this is what, given the hypothesis, this is what X bar should be, right? But at the end of the day, you are actually getting only one sample, right? Suppose this is the sample you have, right? Actual sample you have, right? And if it is here, convert, then you say, okay, that's fine. I don't want to reject. I still want to say mu is A because maybe sampling error, right? Because you do sampling, right? And if it's less than, it's clear that you don't have any support evidence, right? But it's way, way, way above, right? And this probably very small. Then you want to say, I don't want to say it's supporting equal to A, must be somewhat bigger than this. Is that clear what we're doing? Okay. And why we call alpha, remember alpha is what? Alpha is probability that this is true and you reject it. Okay. Because if this is true, you still have possibility that you would end up here, right? That is because we are making a statement that on randomness, okay? So that is happen can be here. So that's why by making some decision on the size of alpha, you will decide where to reject, right? And that is the idea of this alpha, we decide it, and then once we decide it, then we decide where to reject. Is that clear what we're doing here? Okay, so it's just like, then let's repeat because I think that's very important to understand what's going on here. Is, okay, you tell me that the mu is A. Okay, let's believe that. Let's assume it's true, okay? And if it's true, we know sigma, we know that we do a sample, okay? And turn out that this sample is here what we got. And say the green one. The green one is not to exceed from 0, then it's fine. It's less than 0, of course, no problem. But it's way about 0. And the alpha will determine how far we decide is far enough, okay? And if it's exceeding this value, right, this value, right, it's Z alpha, right? It's exceeding this Z alpha, then we reject, right? That's the idea. And alternatively, we call P value is the probability that is, suppose this is the result we have, this is the sample. The P value is the the value that the sample is favorable to x1. Okay, the alternative. So this is the p-value. Okay, there are two ways to do decision, right? Either if this z, okay, if this z is bigger than z alpha, then you reject. Okay, or if this p is less than alpha, you also reject. Okay, either you do it in the C space or do it in the P space. Okay, but let's go to example, then you will see. But before we go to example, is there any question? No? Okay, good. But just to remind you that it's the same as here is we construct, okay? Note that here I looking at this, to put it this way, so I just erase. So the other way around is A here, use A. And remember I convert to Z space, right? This is 0, okay? And here is the rejection region, which is X alpha, right? This is alpha. And if you convert back into the Z space, okay, this is X bar plus Z alpha sigma over N. Okay? Sorry, should be mu, because this is mu here, mu plus, because this is the marginal error. Okay? And so you are checking whether the actual mu is X bar is here or not. Okay? And you see whether X bar is here or not is same as asking whether X bar minus or plus minus ME, okay, between ME and bar is mu inside, okay, because this is ME, right? And you're asking if this, I go the other way around, X bar here, the ME, okay? If this include the mu, then we don't reject, right? Otherwise we reject, because you construct from the mu, see whether it is go to ME both sides, whether bar X bar is there, it's same as asking X bar, you construct the same ME, whether include the mu. Okay, just no repeat. You will reject, okay, if you come from the mu plus ME, right? You're asking whether, for mu, you're asking whether, okay, you reject if X bar is bigger than mu plus ME, right? Because if X bar bigger than mu plus ME, you reject, right? But same as mu is less than X bar minus ME, okay? Because if you have a construct confidence interval, right? This is lower limit, right? The lower limit is included mu or not, okay? So that's why we said the estimation is closely related to the hypothesis testing. It's similar to you construct a confidence interval and see whether this is included or not. Okay, but here is one-sided, so that's why here if you construct the interval, some idea is use alpha rather than alpha over 2. Okay, but anyway, let's see the example, then you will see how we do it. Okay, so as you said, based on the significance level, okay, look at Z alpha. If Z bigger than Z alpha, you reject, otherwise don't. Or you compare P. If P is less than alpha, then you reject. Okay, so I think we just cover that part. So to give you some idea again, right? It's just like if your calculate Z is here, then you reject, right? And this area is not reject. Okay, so just to make sure that is okay. So let's look at the right tail. Okay. Again, we have a standard deviation sigma is 4. How do we know it? Just given. We talk about we don't know it. Okay. Sample size is n is 64. Sample mean is 5. Okay. Now, if before you do anything, if x bar is 3, then actually you don't need to do anything, right? Because if your null hypothesis is more than 4, if you are calculating this is 3, then you are just done because you only concern you more than 4. Okay. So if that, you don't need to do anything. But it's 5, then you raise alarm. You want to see it's more than 5. Is it more than that, right? More enough than what you worry. Okay. So what you do is you construct the test statistics. Okay. Basically, you normalize this, right? Because you are claiming this is 4. Okay. Given that the x bar, okay, this is mu 4. Okay. Now you figure out this is 5. Okay. You want to see, okay, what is this area? Is it small enough? If it's small enough, then it's more than, say, 5%, then you would raise alarm, right? This is x bar here, actual value in front of here, okay? So what you do is convert to a z, right? This is 0 here, okay? And sigma is 4, okay? This is sigma is 1 because normalized. And you convert this 5, what is 5 here? 5 is 5 minus 4, okay, normalized. This is so it should be sigma over root 64, okay, because this is x bar here. So 4 over root 64, okay, it's a, right? 4 is 1/2. 1 over 1/2 is 2, okay? So this is 2 here. Is that okay? Now, once we know 2, then what is number of this? How do you calculate this area? It will be using what we call the T table, right? Norm S inward, because we need to norm as dist, okay? Because we're looking at this side, so it's 2, but you're 1 minus, okay? Let me show you this. Let's do it afterward, okay? Okay, then you figure out this area, and this area we said is 0.22a, okay? Okay, later we do it in Excel. Or you use this idea of 5%, okay? Note that 5% is not 1.96 because it's not 0.25, okay? So how to get this is norm as inward, right? Now it's 5%, right? This is 5%, right? So this is 95, so it's 0.95. Okay, so this will give you this answer. Okay, we'll check these two in Excel very soon, but look at this number, okay? Here is if we have blue, if we want 5%, okay? That is actually 1.64, okay? So that is, okay? of course, you can go back to here to see this number must be less than 5 anyway. But we do notice that this raises alarm, right? Because this, what we calculate is z, right? Is bigger than the z 0.05, okay? So that's why we would be having a concern, okay? So that's why we reject the null, because it is not possible that it is just by sampling. Yes. In this case, alpha, yeah, alpha is 0.05, yes, because one-sided. And later we do two-sided will be 0.025. This is one-sided. The alpha, you put all the property on one side. It's not symmetric. Is it make sense, Peter? Okay. So that is the idea. Why is not 0.025? Because we're one-sided test is only one side. So that's why we reject H null. Because it's not possible, because the probability of this is even smaller than 5%, then it can't be true. Okay. Now I just try to show you why these two are the case. Just to go back to the Excel very quickly. Okay. So we just need to see for 95 as we claim and 2. Okay. So it's norm S and then inward. Okay, it's 1.9449. And this is norm standard. This. One minus. Okay. So that's how we arrive these two. Is that okay? Any question? Why do we need one minus? Oh, because on the right hand side, the very good question. So one asked me why I need to do one minus, because we are looking at the probably bigger than, but the Excel only give you us less than. So the question is why I did the one subtract, because this is equal to 1 minus probability that z is less than 2. This is coming from norm S DST. Is that clear, Kino? Good. Is that okay? We don't need to subtract P from 2. How do you know alpha? Oh, because we are talking about, we are rejecting this at 5% significance level. So that's why we're using 5. Usually you'll be given what is the percentage that is given by the data, given by the question. But usually 5 or 10 or 1%, that is usual. 5% is the most common one. If question in the textbook or in the quiz or exam or assignment, you'll be given exactly what it is, but I didn't write it down. Maybe I should write what is the percentage. Yeah, depends on what you do. Another question is why don't we subtract P from 2? I'm not sure I understand your question. Can you explain a little bit further? P, I don't know, but this is 2, okay? Because look at the z, we are looking at here we want to convert this z to back to the compare it to the 5% one. So what? That's why we don't. This is 5%. Then we know it's 1.96. Okay, good. So 1.64. I'm not sure I answer your question. Is it the thing you want to ask? Oh, we don't need to add back because this is something from Excel. Yeah, no. Okay. I guess almost time, but I just want to show you the other way around that the same. Okay. Here we have quickly, I mean, just forget about this. Okay. So it's less than, okay. And everything the same except before you reject, you put the here, you reject on the other hand side. Okay. So everything the same, nothing changes here, and everything is symmetric on one side or the other. Just flip it, and let's see the example real quickly because the same thing. Okay, just reject on the right hand side. So here I have 4 and 64. X is 3. Right before we have 4, and this is 5, and this is 3. So everything is symmetric here. Okay, instead of so the distance is 1. Okay, and everything is symmetric. You do the calculation again, it will be the same. Okay, but again, don't worry. We talk about this when talk about the two-sided one. But just to saying that whether you put less than or more than, the procedure is the same. If this is two-sided, we put the probability on both sides. But that would be we will reserve it for the next week. Okay, we'll discuss about that. But let's end here. I would be saying to answer any question you may want. But just make sure that you know the homework will be due the next Friday, and they will quiz on Tuesday. So if you don't have any further question, then bye, thank you, and then see you next week. Just remember we have quiz and also your homework. Stay here, answer the question you might have. Someone asked me why I can't have as inward 0.5. You can also 0.05, but it'll be negative. So someone asked me this question. Yeah, this will give you a negative one. Sorry. So if you give this, as I said, it will give you a negative one. And someone asked me that I can use iPad to do homework to you. You can do whatever you like. You can write and scan. You can use the iPad, whatever. I think unless the TA cannot see what you're doing, I think it's fine. Yeah, you can use whatever. Just submit your thing. You take a picture, whatever is fine. I don't. I will type it also fine. Doesn't really matter. Is that okay? So let me know if any further question. I'm happy to answer them. YZ is okay. Very good. So you're asking why? Let me see. your question. Someone asked me why Z is 0.05. Okay, so the question is the following. So remember, we have the mu here, x bar is the mu, okay? We claim mu is certain number, say the question is 4. Kaka, can you see what I'm drawing here? Yes. So the question is, suppose we figure out sigma is, I don't know, 4. So the question is over A, so it's half, okay? And the question here is, okay, now I have the data, which is 5, okay? So now we want to see whether this is enough further away from 4, right? Because we are saying the x1 is mu is bigger than 4, okay? So if it's way bigger than 4, then you would favor this instead of saying mu is equal to 4. Is that okay for this one? Is that clear what we're doing, Kaka? Okay? So then how to decide how greater than 4, right? So we need to determine the significance level alpha, okay? And usually we put 5%. That is a very usual thing to do, right? So that what it means is if, okay, this is less than 5%, then we say this is very unlikely. Is that okay, Kaka, for this one? So we know that this is normal, right? So that's why we can convert it to Z, right, to Z, where we can do this. This is 0, right? We can figure out what is 5% here. Okay, that is Z alpha, which is 1.64. Let me finish this question and answer the t-distribution question. So then, so you look at this, right? This is the Z value, right? Z is bigger than this, right? That means this is less than 45%, less than 5%. Is that okay, Kaka? Do you see what we are doing here? Or you can look at this this area, right? If this area is less than 5%, also you can reject. This is the p-value, right? And we show this is 0.00.2a, then that's why less than 5% also reject. Okay, that's two ways to do it. And there's someone asked me kurtosis for t is bigger than 3 or less than 3. Kurtosis of normal is 3. When the tail is bigger than 3, then it will be bigger than 3. And the t with a fatter tail than normal, so it's bigger than 3. And the other question is why we use 5% but not higher. It's fine. It's just how conservative we want, because alpha is the type 1 error we want to do it. If we think type 1 error is important, then you want small alpha, right? You don't want to you don't want to make the innocent people guilty. That's the same idea. What is beyond reasonable doubt is unclear. What is beyond reasonable doubt? Some people say 10%, some people 5, some people 1, but what is beyond reasonable doubt is a judgment. And in general, we use 5%. If you are more liberal, maybe 1% or 10%, depends on your choice. But 5% is the way standard people use. And there's no particular reason why 5%, but just a rule of thumb. Does it make sense? Let me know if you have any more questions.
唔該，我想問個問題。
好，請講。
嗰個 H0即係假設嗰度啊，個 μ 等於4或者 μ 細過4，嗰個4係點嚟嘅？係咪求其揾個數字？
點嚟咪實際問題啊嘛。
係啊。
譬如話你係做product，譬如話我有罐嘢，話有罐嘢咁啊，佢話佢個糖分係低過幾多嘅，咁咪佢話佢係幾多，你咪 check 佢係咪咯？呢嚿嘢佢 claim 噶嘛。
即係題目已經俾咗啦。
即係呢個係你，即係呢個係即係俾，即係你嗰個 problem。
即係我要做嘅預設係嘛？
係你嘅預知嚟嘅。
哦，明啦。
呢個係問題俾你，譬如話你想睇下你去做 audit，嗰條友話呢個倉庫有%個 mean 係幾多，咁你咪試下幾多，你咪自己睇下咯。
哦，好啊，
呢個
唔該晒。
呢個係俾你嘅，唔使計。
哦。
So the question I have is how you come up with H now is equal to 4. Where come the 4 is? The 4 comes from the fact that is the problem itself, right? Because someone may claim the mu is 4. Okay, you want to check this is 4 or not. So that is the idea. Or product control, quality control, someone said this product contain X amount of nutrient, then you want to check it. Okay? Let me know if you have any more questions. Is that okay? If there's no further question, then I will end the Zoom section. Any more question? Please let me know if you have further question. No? No, then I'm going to end it. So have a nice